Dear student, so in this video we are going to see the numericals or problems which is based on heat engine, heat pump and the refrigerator. That is based on your second law of thermodynamics. So the first problem is a cyclic heat engine is operates between a source temperature of 800 degrees Celsius and sink temperature of 30 degrees Celsius. What is the least rate of heat rejection per kilowatt net output of the engine? So this is the problem. A cyclic heat engine operates between a source temperature of 800 degrees Celsius and sink temperature of 30 degrees Celsius. What will be the least rate of heat rejection per kilowatt if the net output work of the engine? So it is for 1 kilowatt per kilowatt. So what will be the given data? It is temperature T1, which is equals to 800 degrees Celsius. That is in Kelvin, 800 plus 273, that is 1073 Kelvin. Then we have sink temperature, that is T2. So there is always T1 is greater and T2 is less. So this T1 is 800, T2 is 30 degree. So it is 30 plus 270, it is 303 degree. And work output is given. We have to find out this least rate of heat rejection per kilowatt. So your work output will be only 1 kilowatt. To find heat rejection, that is the Q2. So we have this, we have to draw this diagram. So we have a heat engine. So T1 is the source temperature, that is 1073 degree Kelvin, that is the source. And we have sink temperature, that is 303 degree, that is the T2. Then Q1 is the amount of heat which is supplied to the heat engine. Q2 is the amount of heat rejected to the sink. And W is the work output by the heat engine, that is nothing but the Q1 minus Q2 is equals to 1 kilowatt. So we have to find out now for a reversible engineering, the rate of heat rejection, it should be minimum. So we have a formula, that is efficiency is equals to 1 minus Q2 upon Q1. Or we can say, we can have that Q1 minus Q2 upon W also. Sorry, Q2 upon Q1 minus Q2. So you can have a both, that is Q1 minus Q2 upon the Q1. Or we can say 1 minus Q2 upon Q1. So now this heat is directly proportional to the temperature. So we can say that Q1 is nothing but the T1, and Q1 is directly proportional to the T1. Again, Q2 is again directly proportional to T2. So we can say that Q2 upon Q1 is nothing but it should be T2 upon T1. So other parameters are constant. So 1 minus 300 divided by 1073. So we get this thermal efficiency of 0.718. That is 71.8%. So if you have in percent, that is 71.18%. Now you have to find out heat rejection. Now we know that efficiency is equals to work output divided by Q1. So it is 0.718 divided by 1 upon Q1. So we get the value of Q1 as 1.392 kilowatt. Now we have to find out Q2. So we know that W is equals to Q1 minus Q2. So put the value of W. W is 1. Q1 is 1.392 minus Q2. So we get the value of Q2 as 0.392. So this is the heat rejection, that is the at least rate of heat rejection per kilowatt. So for 1 kilowatt, we have this heat rejection 0.392 kilowatt. So this is the first problem. Now we will see second problem. So this is the least rate of heat rejection. Now we have a second problem. For example 2, a domestic food freezer is used to maintain the temperature of minus 15 degrees Celsius. The ambient air temperature is 30 degrees Celsius. So it is the temperature of T1. This is the temperature of T2. If heat leaks into freezer at continuous rate of 1.75 kg per second, kilojoule per second, what will be the at least power necessary to pump this heat out continuously? Now there is a heat leakage and we have to out this heat leakage, pump out this heat leakage. So we have given data that is T2 is your freezer temperature, that is minus 15 degree plus 273. That is nothing but the 258 degree Kelvin. Now we have T1 is the ambient air temperature, that is 30 degrees Celsius is given. So 30 plus 270, it is 303 Kelvin. And the heat leaks to the freezer, it is nothing but the Q2 freezer into the freezer. So it is Q2, that is 1.75 kilojoule per second. That is nothing but the 1.75 kilowatt, because joule per second is nothing but the watt. So we have to find out the minimum power requirement, that is the W. Now we have a diagram. So we have ambient temperature T1, that is 303. We have freezer temperature, that is T2, 258. Now the heat leakage, it is given as into the freezer, it is 1.75 kg per second, that is 1.75 kilowatt. Now here freezer is there, so there we have a refrigerator. So for that we require a W is work input and your output will be the Q2. So we have to maintain this temperature. So the refrigeration cycle removes heat from freezer at same rate at which it leaks into it. So we get for minimum power requirement, we have Q2 upon Q1, that is nothing but the T2 upon U1, because we have Q1 is directly proportional to T1. Again, Q2 is directly proportional to T2. So we get Q2 upon Q1 ratio, it is nothing but the T2 upon T1. Now put the value. So 1.75 divided by Q1 is equals to 258 upon 303. So we get the value of Q1 as 2.05 kilowatt. Now it is in kilowatt, so Q1 is also in kilowatt. Now we have to find out work. So work is again net work output. It is Q1 minus Q2. So Q1 is 2.05, Q2 is 1.75. So your work will be 0.30 kilowatt. So this is the at least power necessary to pump this amount of heat, that is 1.75 kg amount of heat into the freezer. So this is second example. Now we have third example, which is again based on heat engine. Now we have seen one example of heat pump, one example of refrigerator, now one example of heat engine. Now a heat engine receives a heat at a rate of 1500 kilojoule per minute and gives output of 8.2 kilowatt. Determine the thermal efficiency and the rate of heat rejection. So given data is Q1 is given, data heat supplies, or we can say heat engine receives heat. Okay, or we can say the heat supplied by heat source to engine. It is 1500 kilojoule per minute. Now we have to convert in kilojoule per second. That is nothing but a kilowatt. So 1500 divided by 60, that is 25 kilowatt. And output is given, that is work output 8.2 kilowatt. Now we have to find out two things. One is thermal efficiency and second the rate of heat rejection, that is Q2. Now we have this source. This is sink. So the heat energy supplied to heat engine, it is 1500 kilojoule per minute and output is 8.2 kilowatt. And this is Q2 is amount of heat rejected. So HE is nothing but the heat engine. So we have to draw this diagram also. For every problem, you have to need to draw the diagram. So first we will find out the thermal efficiency. Now we have a formula, thermal efficiency of heat engine is equals to work output upon input. So input is Q1, output is W. So 8.2 upon 25. So we get thermal efficiency of 0.328, that is 32.8 in percent. So you have to multiply into 100, so we get in percentage, that is 32.8%. Okay, so this is the thermal efficiency. Now we have to find out the rate of heat rejection. Now we know that W is equals to Q1 minus Q2. Now put the value. W is 8.2, Q1 is 25 minus Q2. So we get the value of Q2 as 16.8 kilowatt. So this is the problem of heat engine. Now we have a next problem which is based on the heat pump. So a heat pump is used to maintain the house at 24 degrees Celsius. The house here, the house is losing heat at a rate of 1800 kilojoule per minute to the surrounding. The heat pump is driven by the electric motor having power rating of 12 kilowatt. So input power is 12 kilowatt. Find the amount of heat absorbed from surrounding and COP of heat pump. So given data, we have Q1 is the amount of heat received by a heat, not heat engine, it is by the heat rate losing rate. So the amount of heat it is losing to the surrounding, it is 1800 kilojoule per minute. So it is 1800 divided by 60, it is 30 kilowatt, and work input is 12 kilowatt. Now we have to find out Q2, that is heat absorbed from surrounding, and COP of the heat pump. So this is the diagram. So there is a house, we have to maintain this out at 24 degrees Celsius. It is not 240, it is 24. That is nothing but the 297 Kelvin. Then there is work input is there, that is 12 kilowatt, and the heat is gets loosed at a rate of 1800 kilojoule per minute. That is nothing but the in 30 kilowatt. Now we have to find out first heat absorbed by surrounding. So we know that W is equals to Q1 minus Q2. So W is 12, Q1 is 30 minus Q2. So from that we get Q2 is equals to 18 kilowatt. So the amount of heat absorbed from surrounding, it is 18 kilowatt. Now COP. So COP of heat pump formula is that is Q1 heating effect divided by work input, that is W. So it is COP of heat pump is equals to 30 upon 12. That is nothing but the 2.5. So this is the another problem. Now we have next problem, that is again a combination of heat pump as well as a refrigeration problem. So a heat pump is used for winter, and air conditioning is used to heat a room to draw heat from surrounding at a rate of 60 kilowatt. The heat pump is driven with the help of a motor which supplies 8 kilowatt of power. So input is 8 kilowatt. Find the COP of heat pump. The same unit, it is used for summer for air conditioning. For that, it requires a 60 kilowatt of heat removal from the rate. For same power input, determine the COP of machine. So given data, now we have Q2 is given, that is 60 kilowatt, and W is equals to work input, that is 8 kilowatt. Now it is for heat pump. So we have to find out the COP of heat pump and COP of refrigerator. So we have this diagram. So heat pump, the work input is this, that is Q amount of heat work input is required, that is Q1. So it is Q1, Q2. So Q2 is 60. So we have to find out Q1. So we know that heat absorbed, it is W is equals to Q1 minus Q2. So 8 is equals to Q1 minus 60. So we get value of Q1 is 68. So COP of heat pump is nothing but the Q1 upon W. So value of Q1 is, that is 68. We have determined this, and W is given, that is 8 kilowatt. So 68 upon 8. So the answer comes to be 8.5 It is the COP of heat pump. Similarly, we have a COP of refrigerator. So it is nothing but the Q2 upon W. So Q2 is 60 upon W is 8. So we get COP of refrigerator as 7.5. Or we can say COP of heat pump is nothing but the 1 minus COP of heat pump is equal to 1 plus COP of refrigerator. So from that we can find out COP of refrigerator is nothing but the COP of heat pump minus 1, that is 8.5 minus 1, that is 7.5. You can take same answer from these two methods. Then we have a last problem. A refrigerator with COP, it is WITH. A refrigerator with COP of 1.6 removes the heat from freezer at a rate of 400 kilojoule per minute. Draw the block diagram of system and compute the power consumed by compressor as well as the heat rejected to the surrounding. So we have given data, that is Q2 is 400 kilojoule per minute, that is 400 divided by 60, 6.67 kilowatt. COP is 1.6, it is given. So we have to find out power consumed and heat rejected to the surrounding. Now it is refrigerator. So the work is input. Q1 is the amount of heat rejected to the surrounding, and Q2 is the amount of the heat removes from the freezer. So it is Q2. So first, power consumption. Now we know that COP of heat pump, COP of refrigerator is equals to Q2 upon W. So from that we can find out 1.6 is equals to 6.67 divided by W. So we get work output or power consumed by compressor. It is 4.167 kilowatt. Now we have to find out heat absorbs. So heat rejected to the surrounding, it is W is equals to Q1 minus Q2. So 4.17 is equals to Q1 minus 6.17. So Q1 is equals to 4.17 plus 6.17. That is nothing but the 10.84 kilowatt. So this amount of heat rejected to the surrounding. So this is the problems which is based on the heat pump, refrigerator, and heating. Now in every problem, the diagram is compulsory. So you have to draw the diagram of the heat pump, refrigerator, or we can say heat engine. And we have only 2 to 3 formulas. So we have efficiency of engine, COP of heat pump, COP of refrigerator, and W is equals to Q1 minus Q2. Otherwise, there is no other formulas. Okay, so this is all about the numericals or problems based on heat pump, refrigerator, and heat engines. So thank you for watching my video, and you will get update based on your this unit updated videos if you subscribed my channel. So the problem will be asked in exam based on 4 to 6 marks. So please subscribe to my channels. Thank you very much.